G'day ladies and gentlemen, and welcome to another episode of What's Up Mate. You're with your host Jake Sparrow from Sparrow Electrical and Refrigeration. This week we're going to have a bit of a chat about cable size, selection, and also the misconception around the voltage drop rating for three-phase and what is allowable as a percentage of the voltage, line voltage or phase voltage, and what's the difference. Voltage rise and how it will affect your client's ability for solar in the future if it is not calculated or thought about correctly in the design stage, now more so that there is flexible export in South Australia where we can look at exporting up to 10 kilowatts per phase. But before we get into it, we will touch base on what we have discussed in the previous episodes for those of you who are joining us for the first time. First up, we had a bit of an introduction into the reasoning behind creating What's Up Mate. Then we dove straight into a discussion around basic testing and verification, something that is so commonly not done and not done correctly in the industry, despite being one of the most important things we as technicians do. Then we moved on to some basic residential fault finding with some handy tips and tricks for the less experienced of us out there, followed up by an episode of how I got into the industry and some tips on what prospective employers look for in new employees and apprentices. Then we covered off really quickly on installing and commissioning split-type domestic AC systems. So if any of them tickle your fancy, have a look through the older episodes and give them a listen. Righto, onto the topic. Let's first clear up some confusion around voltage readings. Phase voltage is the voltage from phase to neutral or earth. For design purposes, this is 230 volts. Line voltage is the voltage from phase to phase. For design purposes, in Australia, this is 400 volts. Put simply, voltage drop is an energy loss throughout the distribution of power throughout your electrical installation. How so? It's pretty simple. If you look at your formulas you learnt or are about to learn at trade school, power equals voltage times current. Super basic. So let's have a fixed load of a very simple resistive load, which gives us a power factor of 1. Voltage at the load end of the cable times by the current measured through the load equals the power. In this example, let's use our 230 volt design voltage and a fixed resistive load of 10 amps. So 230 volts times 10 amps equals 2,300 watts or 2.3 kilowatts. Now, let's use a lower measured voltage of 228 volts at the appliance. So 2 volts less than what we had before. So 228 volts times 10 amps equals 2,280 watts or 2.28 kilowatts. Now, the difference between 2.3 kilowatts and 2.28 kilowatts is only 20 watts. But where has the 20 watts gone? It's simple. It's been dissipated as heat within the cabling supplying that appliance. Okay, but what about if we are doing a calculation, we know the resistance of the load, but we know our voltage will fluctuate throughout the day due to solar or loading on the street? Well, let's look at the calculation as a resistance formula. Power equals voltage squared divided by the resistance. So let's say we have a resistive load again of a fixed, easy to calculate value of 16 ohms. And our measured voltage of the system is 230 volts at the terminals of our appliance. The power of this is 230 volts squared, or 230 volts times 230 volts, divided by 16 ohms, which gives you 3,306.25 watts. But again, if we reduce our supplied voltage to 228 volts, we get 228 volts times 228 volts, then divided by 16 ohms, which equals 3,249 watts. In this scenario, we're losing 57.25 watts within the cabling of the installation as heat. Now, we don't want excessive losses in our system as it's just a waste of money. However, we don't want to run huge conductors everywhere to limit voltage drop, because it is an expensive outlay for our clients. And let's be honest, who wants to be terminating 6mm into your lighting terminals? It's just not practical either. So with AS3000, they've specified that the total voltage drop across the installation to be 5%. This is just a happy medium between wasted energy and cable sizing. Now we know what the impact of voltage drop is. How can we calculate it? Well, To do this, you will need to have access to some Australian standards, which, as an employee of an electrical contractor, you should have access to all the standards, and also as an apprentice, you should have access to these either through TAFE or through your employer. They are quite expensive, but they are super worth it because they are sort of form up part of your toolkit. So the two that we're going to specifically need for voltage drop and voltage rise calculations is AS3000, which is obviously the wiring rules, and AS3008, which is the selection of cables. Now, to calculate voltage drop, there are two ways. So we've got the calculation method, which is where we enter values into formulas, which we get out of a tabulated book, which is AS3008, or the measurement option, which still involves the formulas, except we actually are on site measuring actual voltages, and you will probably use this one a little bit more for pre-established factories, homes, etc., where we've already got fixed line voltages and things like that. Right, for the calculation method, this is more so for calculating new installs where you don't know exact loads, but you've done your maximum demands calculations, or you know the circuit protection rating for your loads, so you can have a safe bet, for example. Calculating voltage drop along a general power circuit with, let's say, 2.5 twin and earth cable and a 16 amp protection device, you will actually divide the rating of the protective device by 2, so that'll give you 8, and use that for your current rating of the circuit and your voltage drop calculations, because the load is spread across the entirety of the circuit. But for a load at the end of a circuit, you will use the full rated current of the appliance because the load is at the end of the circuit. So examples for that may be a spa, hot water service, air conditioner, oven, cooktop, etc. So there's a few little oddities around this as well. For items such as like welders, where they are drawing constantly fluctuating current, stop-starts, and the end user is actually adjusting the power of the appliance. Personally, what I like to do is I recommend calculating the voltage drop 1.5 times your rated current of the welder, for example. A 20 amp welder, I would allow 30 amps for my voltage drop calculations. The measurement option is when we measure your current, voltage and power factor using a logging device, and then use these values for your calculations. This method is used to determine existing realistic values to enter into your formulas, and is more accurate, however has less of a safety margin. Now, what affects voltage drop? Well, the size of the conductors, the type of the conductors, so if we're looking at aluminium versus copper, the length of the run, the load, and also the voltage. Now, the bigger the conductor, the less resistance, which means less voltage drop. The more conductive a material, the less resistance, which means less voltage drop. Aluminium is cheap and is often used in long rural runs. However, it is not as conductive as copper. Personally, we use it all the time for this purpose. However, we need to ensure that we increase the size of the conductors when we use aluminium compared to using copper conductors. Again, it's a good little calculation to do to see if you can save your client some money, and aluminium's much lighter to work with than large copper. The longer the run, the larger the resistance of the cable. So you'll need to increase your conductor size to combat that. How much of a load do you have? The more current flowing through your conductors, the more voltage drop you will have. Now, let's do a little bit of an experiment. If we rolled out 100 meters of 2.5 twin and earth, and we applied 230 volts across active and neutral at the start of the roll, at the end of the roll with no load, we would have 230 volts at the end of it. As soon as we start to add a load to that, that's when our voltage drop will become apparent. Supply voltage now, because we state our voltage drop as a percentage of the supply voltage when designing it, is 230 volt or 400 volt for balanced 3-phase loads. But if we are using the measuring method, we can calculate based on actual values we've recorded. So things we can easily manipulate to affect voltage drop is the size and the type of the conductors. Everything else generally is like the load and the voltage are generally fixed figures, and we don't have a lot of say in that. So how do we put all this into practice? We need to calculate our voltage drop from our supply point, from our supply authority, maintaining in all cases a maximum of 5% voltage drop. So in South Australia, that's SA Power Networks. This is the start of our consumers mains to the end of our final subcircuits, which also includes the consumers mains to the meter board, from the meter board to any subboards, and then to the final subcircuits. In commercial or industrial, you may have many subboards within the installation, so you need to do multiple calculations for all the submains. There is the old-fashioned way of using the books and provided cable sizes and resistances as well as formulas, or you could use a voltage drop calculator such as Cable Pro, which is what we use. However, it is important to understand the manual calculation method so that you grasp the concepts before plugging values into a software system. Because we're using a calculated percentage of a voltage, we can actually add each percentage together to get our total volt drop as a percentage. So it's quite an easy thing to do once you've determined your voltage drop as a percentage for each part of your installation. Now, the misconception on using 400 volt in your calculation is a big one and is everywhere in our industry. We see time and time again in rural applications mainly, and have had a very bad scenario of poorly designed installations. One that springs to mind straight away was a rural place in Echunga. We've basically got a long 3-phase run. Solar guys installed 3 separate single-phase inverters. So we basically had a single-phase inverter on each phase. So it wreaked havoc on their equipment and left them with all sorts of issues on their 3-phase equipment, specifically their hydronic heating systems. Basically, all the smarts in that picked up that we had unbalanced voltages and shut itself down. So they were without heating or hot water for quite some time. So, big misconception, and I'm not sure where it stems from, whether or not it's not taught correctly at school. It's basically, I've got 3-phase, so I can use smaller cables for my mains or my sub-mains. I'll save the client money. Wrong. A sub-mains or consumers mains is very rarely, or if ever, actually a balanced 3-phase load, and the only time we can use that 400 volt figure is on a balanced 3-phase load, which basically means there's no current flowing in the neutral conductor. So if you don't have a balanced 3-phase load, you need to actually calculate that voltage drop for that run at a 230 volt value. So therefore, we're going to get less permissible voltage drop, because 5% of 230 volts is a lot less than 5% of 400 volts. So we're going back to using larger conductors. Bummer, right? Well, no. Bigger conductors have their benefits, such as lower fault loops, less voltage rise, and to be honest, look a lot cooler when you're terminating them. So when can we use a 400 volt or 3-phase voltage drop calculation? Again, the only time we can use a 400 volt or 3-phase calculation for voltage drop is for a balanced load. Balanced 3-phase loads, things such as motors, and we can't actually use the 3-phase calculation for the whole installation, but only for that particular circuit supplying the 3-phase equipment that is balanced. So if you think about it, it's going to be quite rare in a domestic or a commercial installation to use a 3-phase voltage drop calc. We've used 3-phase calculations for motor control cabinets, or more recently for a cable calculation we did as part of an installation with 3-phase ball pumps. So when calculating, make sure you're actually using 230 volt, not 400 volt, unless you are, of course, a balanced load. Cool. So that was voltage drop, very briefly. Voltage rise. What is it? Well, voltage rise happens when we have a generation source, such as an inverter or a generator, generating energy and feeding into the installation or the grid. Now, voltage rise is calculated using the same method and formulas as voltage drop, so nothing new to learn here except the concepts. So voltage rise is the direct opposite of voltage drop. So it must be a good thing, right? If voltage drops, there is a loss of energy. So if voltage rises, well, that must be an increase of energy in a circuit, right? Yeah, not a bad way of thinking of it, but it's not a good thing. Let's have a look at a 5 kilowatt single phase inverter exporting 5 kilowatts to the grid. Using our formula of current equals power divided by voltage. 5 kilowatt at 230 volts is 21.74 amps. So let's increase that voltage to 240 volts. 5 kilowatts at 240 volt is 20.83 amps. So for the same power, we're actually have less current flow, which has its benefits. But we have rules around how much voltage rise we are allowed, and that this is for a number of important reasons, with the most important being grid voltage stability and grid voltage range. An inverter will always increase its voltage to output power back to the installation or grid. If the voltage was less than that of the grid, it would not be able to push power into the grid and it would actually become a load. However, if everyone's internal voltage rise in their home was excessive, the grid voltage would rise too high and we would end up with another statewide blackout. Not common, but we've had a few in SA in recent times, mainly due to damaged infrastructure. However, grid voltage rise had to be controlled by SA power networks until the grid could be repaired. So to calculate voltage rise, we need to look at the same contributing factors as that of our voltage drop, which were the size of the conductors, the type of the conductors, the length of the run, the load, and also the voltage. Now, there's a difference in our voltage rise allowable percentage. So with voltage drop, we were allowed to drop 5% from our supply voltage. With voltage rise, we are only allowed to rise 2% from our supply voltage. This is to combat grid voltage rise, which is a complex calculation, which we won't get into on this episode, and frankly, it's a bit beyond your scope as an electrician. So to look at voltage rise, we need to look at a few different things. Inverter capacity, inverter location, is it feeding into the install at a meter board or a subboard, and also what loads is that inverter supporting. We've also got to look at things like export limits on the site. Some might have a 1 kilowatt export limit, some might have 0 export limit. In SA, we're moving up to 10 kilowatt per phase on a flexible export solution. And we've also got to look at whether or not we've got smart metering, etc. So let's have a look at a common scenario in a domestic home. Inverter is located right next to the meter board and wired directly into that meter board, not going through any subboards. It's a 10 kilowatt single phase inverter with a 5 kilowatt export limit using a smart meter to do this. The voltage rise calculation is the voltage rise in the inverter submain cable to the board using the full inverter capacity. Let's say we have a 10 kilowatt single phase inverter. So voltage rise calculation for the solar submain is calculated at 10 kilowatt and the voltage rise for the consumer mains is calculated at 5 kilowatt. Now, this is because your inverter is going to ramp up past its export limit when the house is using power. Let's say you're boiling a kettle, or you've got your air conditioner on during the day, or you're doing a load of washing. So all we need to do is add those two percentages that we calculate to get your total, and it must be less than 2%. So perhaps your consumer's mains is small, like 16 mil, bare bones, basic, and you need to oversize your inverter submains to combat the rise. Or if you can't get the desired result, you may need to export limit the inverter further. Or perhaps a battery will be the better solution, so you're not exporting anything to the grid. It will all be site dependent. And if you don't, not the fellas or the girls doing the solar, perhaps have a chat to the client and maybe have a chat with the solar guys doing the install. This way we can make sure that everything's going to work seamlessly for the client and just make for a real smooth install from both ends. So let's have a look at something a little bit more complex and look at a meter board on a rural property. Now, the meter board is about 400 metre from the solar install, and the meter board supplies all the outbuildings, including pump station, homestead and sheds. The solar install is on one of the large sheds. The homestead also supplies a large cool room. So now we have multiple loads spread across a large site. Solar install has been designed to offset the whole of the farm's energy use and is a 45 kilowatt system using three 15 kilowatt three-phase inverters. So we are looking at a 15 kilowatt per phase, which is approximately 65 amps. The site is export limited to 10 kilowatt per phase, which is approximately 40 amps. It's a simple calculation, just a few extra calculations to do. So we need to calculate from each inverter to the solar subboard on the shed. Each inverter generates 5 kilowatts per phase. Then, at the solar subboard, the sum of the inverters per phase, which is 15 kilowatts per phase, 65 amps approximately. We use an unbalanced three-phase calculation to determine the voltage rise in this scenario because we cannot guarantee there are no unbalanced loads being fed from the shed board now or in the future. So we need to calculate voltage rise from the solar subboard back to the meter board at 65 amps per phase at 230 volts. Now, the meter board to the point of supply will be calculated at the site export limit of 10 kilowatts per phase. So we're only looking at that at about 40 amps from the meter board back to the point of supply, whereas between the meter board and the solar subboard, we've got to look at that full 65 amps per phase. Now, we don't need to calculate the voltage rise back to each other subboard at the homestead or the cool room because they become voltage drop calculations as they are loads and not sources of supply. So we can ignore them because we don't have a source of supply feeding back, if that makes sense. So as you can see, sometimes voltage drop may not be the only concerning calculations you need to do when designing an electrical installation, and voltage rise from generation sources is a large concern too. In our experience, it's always best to have a chat with clients about their future solar ideas because you can almost guarantee you they're going to want to put solar on their new house or on their farm, etc., even their sheds. So this is just a basic overview of voltage drop and voltage rise. Hopefully it's raised a bit of awareness of your requirements as an electrician around both voltage drop and voltage rise calculations. So next time you're at a client's house doing a bit of a walkthrough or discussing with your boss about a job that you're doing, etc., maybe let's have a sit down, have a think with the other Sparkies in your crew and have a chat about voltage drop and voltage rise. Now, obviously, these are not the only calculations that we need to factor in. Other ones that we need to factor in are obviously things such as fault loops when designing a system, so making sure our resistance is low enough in those cables to ensure we've got automatic disconnection of supply in the event of a fault, especially for submains, etc., where we can't rely, not that we do rely on RCDs for automatic disconnection because RCDs fail, but it's a very important measurement and calculation we need to do. But as a rule of thumb, if your voltage drops, sweet, for domestic especially, generally your fault loops are going to be pretty well close. The only time we've ever really had issues is when we start to parallel up conductors, so just be really mindful of that. Obviously, you're going to calculate your fault loop and you're also going to test it. We just need to make sure 100% that that's correct. So thanks for listening, guys and girls, to another episode of What's Up, Mate? By an Aussie Tech for Aussie Techs. Thanks again for listening, guys and girls. If you enjoy listening to my podcast, certainly would invite you guys to have a look and get some visual references to what we get up to at Sparrow Electrical and Refrigeration. Instagram is at Sparrow Electrical. Facebook is just Sparrow Electrical and Refrigeration. You'll see us there pretty quick. Currently, we are looking for a tradesperson and also a general manager or a sales agent. Now, if you know of anybody that fits the bill, want to work for one of the leading electrical and refrigeration companies in South Australia, I would love to be put in touch with them. So whether it's yourself or somebody you know, please reach out. We would love to have you on the team. Thank you. We'll see you next week.